Hi, welcome to Lab 6 of the Serverless Machine Learning course. This lab is going to be on real-time machine learning and a little bit on how to organize your machine learning projects. So we're going to start by looking at keeping your house in order. So what should a good directory structure look like for a machine learning project? We've kind of put together different parts of our machine learning system throughout the different labs. We've done feature pipelines, training pipelines, inference pipelines, notebooks, Python programs. So how should we put it all together? We'll cover that first in this lab. And then we're going to look at deploying a model, and we're going to deploy the model in Hopsparks. We're going to create feature pipelines that write to the online feature store. So those features will be available by the model deployment. The model is running in the model serving infrastructure. You'll be able to retrieve features from the online feature store to build feature vectors in near real time and use those feature vectors then to make predictions. So we'll be able to use historical and contextual features to make predictions, which is great. So let's get started. Let's do the usual. We're going to retrieve any changes in the Serverless ML course since the last time you've pulled. So you just want to call git pull from upstream main, assuming you've called your your upstream the course's repo, GitHub repo. And let's get started. So let's have a look at how do we organize an ML project. Now this is just a recommended directory structure. Of course, you're free to use your own. But I think we've learned a bit throughout the course that having your house in order and being able to organize things, so being able to put different pieces of code into different pipelines, so you could have a feature pipeline, a training pipeline, an inference pipeline, it helps scale our systems and it decouples the different parts so that they can be developed independently but also operated independently. So what we're going to look at are some of the different proposed directories that you could have in your project. Now this is what we see in module 6. We have a directory called notebooks, and this is where we're putting our Jupyter notebooks. And the notebooks, in our case, we've used them as actual pipelines because we've been able to run them in GitHub Actions by converting them into Python programs and then schedule the Python programs to run. Here we're going to put them in a separate directory here. We're going to include a requirements.txt file as usual. That's going to have all the dependencies that this project will need to be installed. You can see it's going to be a slight difference here. You've got a setup.py file and a directory called my module. So we're now going to put all of our Python code into a directory called my module. Now my module is just the name I'm giving for my module. If you're creating a module called Serverless Machine Learning, you may want to call that directory Serverless Machine Learning. The setup.py file will contain details about the Python module. We'll look at that in a second. But inside our Python module, we're going to have some different directories for some of the different things that we want to do with our code. So you might want to create pipelines, for example. So feature pipelines, training pipelines, or batch inference pipelines. And those are going to be Python programs. So we can put them in this directory called pipelines. Features that we use to create features. So Python functions, UDF, user-defined functions, to create features, and also Python user-defined functions used to do model-specific transformations. So maybe it's going to be a Python UDF that you define that you're going to one-hot encode a categorical variable with. A custom one, because of course there's many of them that are off the shelf, but this is for custom model-specific transformation functions. And that'll be another directory. Tests for your unit tests, particularly for your feature and logic, but also for transformation functions. Pipeline tests, so end-to-end tests for running your pipelines. So if you have a feature store, you'd connect your feature store, then run your feature pipeline against the feature store. And then finally, visualizations. And visualizations can go inside your module. Maybe you want to put it outside the module. It's up to you as to how they're used. They may be used in your programs. You may be producing visualizations as part of your feature pipelines or training pipelines, and then you want to export those, for example, to your model registry or to to your feature store, where they can then be used as part of the analysis of the program run. But of course, that they may be not part of your production system, so you may move them to a top-level directory. And then finally, scripts. So we saw that we had some scripts that were used, for example, to convert a notebook into a Python executable program that we could then run as a GitHub action. In general, any bash script you need, and this might be for things like running tests or running pipelines, you can put into a scripts directory here. Now, there's a little bit more meat on the bones in here. This is the same as we had before. You'll probably need a README as well. In your notebooks directory, they should be the ipynb files. Inside your module, you'll need an init.py file. That's basically for example, to find the version of your module. You'll put that in there. Your features directory and your pipelines directory and transformations directory, they'll all have just Python programs. So they're going to be Python modules inside this package, this directory. And the same for tests and pipeline tests and visualizations. So visualizations may or may not be Python programs. Typically they're notebooks. But you know, depending on how you're generating your visualizations, they may or not be notebooks. Okay, let's go in and have a look at that directory structure now while we're here. I'll just go back to my terminal. So this is my terminal here, and this is the directory structure we discussed. Now you can see it's not called my module, I call it SML here, Serverless Machine Learning. There is actually already a PyPy package called SML, so you might want to rename it to something that's not in PyPy. But this is my Python package here, or the Python package that I can install. And if I look at the setup.py file, you can see here, I give it a name and a version, and then the package name, so it's the directory where all the Python files are, a license and a description. Now, like I said, I won't be able to deploy this to PyPy if I wanted to, because there's already a package called SML, so I'd need to change the name. But if you have dependencies as well in your package on other libraries, you'll need to include them in here. You'll find plenty of good information on the internet for how to write a setup.py file. So if we look at the rest, we've got a requirements.txt file. There's nothing in here, so we should have something in here. Let's have a look. We need hopsworks at least, and probably we'll need to add more to that over time. And then if we go into our SML directory, and we have a scripts directory as well where we can put our scripts. But in the SML directory, we have the init file for our module, our Python module. We have some features. So in here I have some features. These are credit card features from the previous labs. So the ones for creating synthetic data and one for creating features from that synthetic data. Inside the pipelines, we have a Streamlit app and a Streamlit batch app. You can try those out. We have in the tests, we don't have anything in there currently, and then in the visualizations we have nothing. So we can add code as we want to into these different directories, and I'm going to get started by so there is, for example, a unit test for our features we covered in lab number 2, so you're free to put that into the test directory, and then you can run PyTest against that unit test, and you can add more features to functions. So the functions that you use can be as features, you can add them as unit tests to your test folder. Okay, I started Jupyter Notebook already, so let's pull that up. And we can see in here, these are the notebooks that we have to cover today. There's quite a lot of them. And I'm going to start by opening the CC backfill features. We've covered this one before. What you'll see that's slightly different in the notebook today is that you can see here that at the beginning, in the notebook, I'm writing cd dot and pip install e. So in fact, this should be cd dot dot, shouldn't it? So let's have a look at this. So what I want to do is basically install my SML Python module. So let's go back here and look at it. So when I'm in the notebooks directory here, what we can see is that, let me just remove this. I have a symbolic link, I think, to SML. Let's remove that, or SML. Okay. So what I want to do then is from my notebook directory, I'm going to change to the parent directory, and then I'm going to, actually I need to change to the SML directory, don't I? It's going to look like this. And then I'm going to install this SML Python module. So by changing from my notebooks directory to the SML directory like this, if I type pip install -e dot, it will install, oops, it's in the wrong directory. So install -e dot. Okay, so it's actually the parent directory. I'm sorry, I'm slightly confused here. So you can see here it's installing my SML directory, so that should be, that was correct. Okay, and that's the reason for this is because we can see actually that the setup.py file I forgot is in the parent directory, so it's not in the SML directory itself. So it's going to look for this setup.py file. We get the name of the package we want to install. We didn't need to put the name in here because it was found in the package, and then it installed it. Now -e, what that does is it creates a link to the directory. So if I make changes to the SML, to the files in the SML folder, I won't need to reinstall the package to get those changes, which is great. That's what I want when I'm developing. Okay, let's move on. We're going to import some more packages. Another thing you can do, just in case you're curious, is you know, what we did earlier was we created a symbolic link, or we had as a subdirectory the SML folder, which had our Python modules in there, and that works fine. But if you need to maybe move that directory to some other folder, maybe in your inference pipeline, it's going to be in some other path in the system. Another way to get access to that, or add that particular package to your path, to your Python path, so that it's able to be picked up and used in your notebooks, is to call the following: import sys, import os, and then just call sys.path insert, and then it's going to take my current directory and then go to the parent directory. So that would then have my parent directory added to the Python path, so then I could use the SML module from there. Okay, so here's, because we imported the SML module and features is now a subdirectory, we can't go from features import synthetic data, or from features import CC features, which we did in labs 2 and 3. We're now going to call the name of the Python module, and then the subdirectory features, and then we're going to import the synthetic data and CC features modules from that directory. So let's remember the terminology. So a directory is a package in Python, so SML is a package, and then we have features, which is a package, and then we're importing this CC features module and this CC synthetic data module in here. Now the code is the same as before, and we do some feature engineering. We've done some more here. I left out the excuse me, I left out the Great Expectations code in here. And the only thing we're doing slightly different is we're now changing this line when we create the feature group. We're setting online enabled to be true. And the name of the feature group is slightly different. It's called transactions_fraud_online. So now when I create this feature group, we'll have both an online table and an offline table. And we're inserting some data into the feature group. We're creating another feature group called transactions fraud label online. So we've got the fraud online and the label online, and then we're finally going to have the latest recorded transactions fraud online. And we have another one here, profile fraud online, and CC trans fraud for hours, which is also again online. So you can see we have quite a lot of online tables that we've created here. So we've got 1, 2, 3, 4, 5. One of them to note is in fact that what we're going to have to do is we're going to have to store, you can see this particular one called latest recorded transactions fraud online FG. This is really a helper feature group. It's going to be used to store the most recent transaction coordinates for a given credit card. And we're going to need that, in fact, when we're computing the haversign distance in an on-demand feature. So one of the on-demand features is, hey, I got a credit card transaction arrives. I'll get the, within that application information, I'll have the longitude and latitude of that credit card transaction. It'll only be supplied by the application. But to compute the haversign distance, I need also the most recent longitude and latitude transaction for that card. So what was the most recent transaction on that card? Give me the longitude and latitude for the most recent one. Then I have the current one, and I'm going to use that then to compute the distance between those two credit card transactions, the haversign distance. So this is basically a helper table that we're going to use just to store the most recent credit card transactions for all credit cards. It's not going, we're not going to use it for training. It's just going to be used for the haversign distance function. So let's go over and have a look at the feature groups that have been created. And we can see here that we have our transaction 4 hours. We can see also this little green sign which says it's online. So the feature groups we created before were only offline. It's this black little icon here. And these new ones, 1, 2, 3, 4, 5, they're all online. So if I click on any one of these feature groups, they look the same as before. The only difference is they're called online. We can see we haven't configured too much for expectations, alerts, or tags. We can click on preview data, and in this time we can see we can preview both from online or offline. So I can click on offline. It'll then make a query on the offline feature group. It's a little bit slower than the online feature group, you can see. But that's basically it. So we have got our feature groups back here. Let's go back and look at the next notebook. So next notebook will be here. It's notebook number 2, and it's the same as before. This is the we can think of it as a production feature pipeline. We've already created the feature pipelines in the backfill CC feature group notebook, and really these are no different from before. The only difference here is that when we're importing our synthetic data and CC feature modules, we need to do it from the sml.features package. And otherwise it's the same as, this is the same as lab 2. We've a little bit new code here. We've got this latest recorded online feature group. We're going to insert the transaction coordinates for the most recent ones in there. But otherwise it's the same as before. Now, yeah, we also have a separate production feature pipeline for computing the aggregate features. So in this one, you can see we've got a reference to transactions fraud online, and we've got the aggregated features computed here, and we're writing them into the feature store here. So let's look. So then we've got a few more notebooks to go through. We've got the feature view creation notebook, and in this one, again, I'll just have to fix that to make it CD. I think all of these actually need to be fixed. Don't worry, I'll push the changes to GitHub so that you won't have to worry about it. Okay, that one too. And here we're creating, you can see we're creating a feature view, quite a large feature group here, feature view here called, this is the latest recorded transactions online. We're going to need that one online to get the latest position or longitude, the longitude and latitude of the most recent credit card transaction for a credit card. And this is, we're creating the feature view from that feature group, but we're also creating, you can see that's this one here. But we've got, if we look at the actual query for creating it, it's selecting a lot of features. So we've got one from the label feature group, the fraud label, the transaction feature group. We've got some transactions, we've got the window aggregations, and the profile online. So there's quite a few going in there. And yeah, so then we've got this latest recorded transactions, and this one is the okay, sorry, this one I can see the name of this one actually should be that. It should be transactions fraud online FV. So we've got two feature groups, the feature views there. One is the latest recorded ones, but the other one actually is the transactions fraud online FV. So once we've created those two, what we're going to do is we're going to create a time series split. We're going to create some training data with the start time and an end time. This code looks a little bit complex here, and in fact in HopsWorks 3.1 there'll be a nicer API for creating training test splits. But at the moment this is the code that we have to do it. And here we're basically saying start training time at this time, and the training time ends at this time. So that means effectively that the test data will start at a different time, and the test data will end at a different time. So we're going to have two different, we can think of them as training sets and test sets. So this is our training set here, and this is our test set here. So we create those. Now let's go back and have a look. Those are being created. So this is the transactions fraud online FV. So this is all the features we want to use to train for credit card fraud. You can see we've got the same ones that we had in lab 2, and I've created training data, a couple of them. You can see I've created the training set and the test set. So I've created two different training data sets from it. So in fact, this is not a training data set, it's a test set, and this is a training set. Like I said, currently this is the way we're using it for time series splits. Okay, so now we've created our training data. We want to train our model. And this is going to be pretty straightforward code, same as we've done before. We get our feature view for to the fraud online FV feature view, and then we're going to get the training data and the test data from it. We're doing it here, and then we're going to train the model. It's going to be a very simple XGBoost model. And you can see we're fitting it on the training data from March to August. And then when we want to evaluate it, we're going to test data will be for September. So the model itself, you can see the performance, it's quite okay for true normal. So they predicted that it wasn't fraud, and they were correct. Predicted that it was fraud, and it was actually fraud, was 3. But then was predicted fraud and it wasn't fraud, we had 16. And then where it was predicted that it wasn't fraud, but it actually was fraud, we had 10. So this model is not great, but it's a reasonable starting point. So in particular, we want to avoid the ones where we predict that the transaction is not fraud, but it actually is fraud. So this one should be we should modify our F1 score to basically heavily penalize this particular set of false negatives. The false positives up here where we thought it was fraud, but it wasn't really fraud. Yes, they're inconvenient for the people affected, but maybe not as expensive from a compliance perspective for a bank or a financial institution. Okay, so here we're doing a bit more here, and then we're going to register our model with Hopsworks, the same as before. So after we register our model, the model will appear in Hopsworks. We can see it here in our model registry. This is the Transactions Fraud Online XGBoost. And you can see this is version number 1 here. And we can see that this, and I said the F1 score that we have here is not very useful, because we want to obviously adapt it. You should in production adapt it to basically heavily penalize false negatives in this case. And then finally, we're going to deploy the model. So I think we need to go to another notebook to deploy it. So this is notebook number 5. So notebook number 5 here, and again, we need to install the library correctly. What we're going to do is create a prediction class. So this is, in this case, in Hopsworks, when we deploy a model in Kserve, which is the underlying model serving infrastructure in Hopsworks, when you have a scikit-learn or an XGBoost model that we have here, an XGBoost model, what we need to do is implement this prediction class. So we need to implement the predict method and the init method. The init method is called once when the container is loaded for the first time. So what we're going to do at that point in time is we're going to load the model from, in this case, there's an environment variable called artifact files path. So this will basically contain any files in the model registry directory, and we can go back to our model and have a look at what's in there. I'm just going to go back to the model. This is our model here. So you can find that out in here. You can see this is the model that's actually deployed. But if I click on Browse Model Files, it'll bring us to the directory where the model is actually stored. It's this XGBoost pickled Python file. We see we have a couple of other JSON objects in here. This is the schema for our model, and then an input example as well. And then we have some other artifacts. You could have merchant artifacts in here as well. Let's have a look in here. In this case, you can see we have so these are the ones that will actually be deployed then, and you'll be able to get from that environment variable that we saw. So remember, the environment variable is artifact files path. So in this case, we'll have the XGBoost, and then this predictor function that's this one that we're writing here. You can see this one here, predict example.py. That predictor dash, and then the name of your file, predict example.py, is what gets deployed then in your model serving infrastructure. So in here, we're loading up the model from this directory, environment files path, and that's complete. What we also typically you might want to do as an exercise here is, if you have a feature view that you need to get a feature vector with, then you might need to connect there to the feature store in the init method, and then call init on your feature view with the training dataset version that was used to train this model. So, and then in your predict method, you can just call self.model.predict with the inputs as they come in here. So in this case, we just have to reshape the inputs, and then we're going to return a list as the output. Okay, so this example, what we're doing is we're in the notebook is actually creating this predict example.py file, and then we're uploading it to that models directory that we saw here before. Okay, so now you could also create this in your training pipeline and add it to the directory locally. when you're registering the model, we could have done that earlier as well. Let's look at how we create the deployment. What we need is a reference to the model. So we're going to get that by getting a reference to the model registry first, and then getting our model. And this is how we're doing it here. And then we just call model.deploy. And in this case, the model server we're using is Python. That's what we use for XGBoost, scikit-learn. There's one for TensorFlow and one with PyTorch coming soon. And then this is K-server we're deploying with, and then the predictor script that we just created here earlier. So this is our predictor script. And the path to it is defined up here. You can see that's our path to our predictor script. So when you call model.deploy, it will get added as it'll be created as a deployment here. These are deployments here. Now it's currently status is running, but when you deploy it at first, it won't be running. So when you call describe on it, it'll basically say it's initialized or created. We need to call start on it in order for the model to get to actually start running, and then we can get the state of the model and you can see if it's running or if there's a problem. You can also call get logs to get the logs. Get logs only works, however, if the model is running. So if the model is not running, it won't get the logs, because what it's doing is it's going to look in the container. If there's a problem with the container, then get logs won't work. You can also, if you go back to your deployments here, I can go back actually to where we were before. You can get your logs here as well. So you can get metrics and logs for your models. And this gives you a Kibana or OpenSearch dashboard UI for accessing your logs to your model. Okay, let's go back and have a look. Now, so this is how we deploy the model, and my model's already been deployed and it's running. You can see here. You can press run test to test your model. You get the endpoints, see the schema and some code snippets for how to use it. And then the resource allocation. In this case, I've got 1024 megabytes available and about half a CPU. There's not a huge amount of resources, but probably enough just to handle some small number of requests per second. And then we've got some Grafana charts showing you the number of requests per second on your model. So that's it. We've deployed the model. So let's have a look at actually using it. And this is notebook number 6. We can see what it's doing is it's going to start. Let's start this one running because I'm actually going to use it. So we need to get a reference to our model. It's already running, so this should tell us it's already running. Okay, so it's connecting to Hopsworks at the moment and getting a reference to the model serving. So MS is the model serving. And then I called start and said, well, it's already running. Okay, fine. Let's have a look at the logs. We can click on that to look at the logs, and now we'll get a reference to our feature view. So in this case, we're getting a reference to the feature view because we're going to get some pre-computed features from the feature store and add them together with the features that arrive for a credit card input request, and that will build up the whole feature vector that we're going to make the prediction with. So you can see here now, it takes like a couple of seconds to connect to the feature store, or feature view, I should say. And then we have this method here called process input vector. And what process input vector is, it takes in the application supplied features. So when you use your credit card, it's going to have a credit card number, the current date time, the amount being spent, the longitude and latitude for where this credit card transaction took place. And what we see we're going to need to do is we're going to get the pre-computed features by calling feature view.get feature vector with the credit card number, and this will give us our pre-computed features. But we then also have the on-demand feature view that we need to compute the haversine distance. So to compute that, what we're going to do is we're going to call our on-demand feature function, haversine distance, from our Python module. So this is the version Python module. It should be the same one that you used in your training or feature pipeline from earlier. And we're also going to do the same for the time delta and time delta today's, which are also on-demand features. And you can see here we're passing in the current longitude and latitude as well as the previous ones. So we've gotten those when we called get feature vector. That included the most recent longitude and latitude for this particular credit card transaction. So now we have all of the features that we need. So we've got our we've got our on-demand features, and these came from in this case the the latest recorded FV. We latest recorded FV feature view. We got the most recent longitude and latitude for the most recent transaction. Prior to this one, we've now computed our on-demand features, and we're going to get all of the features, the rest of the pre-computed ones. So these two are computed were the on-demand features, location delta t-1 and time delta t-1, but amount just came in from the application. So we call all of these collectively past features, so that what this basically says is that when I'm getting the feature view from, in this case, the feature view is the transactions fraud online feature view, it's saying I don't need to retrieve these from the feature store. The amount, location delta t-1, and time delta t-1. So these ones are being passed. Two of them are computed here on demand, and one of them supplied by the application. And altogether, that will give me the full feature vector. And that feature vector is what I'm going to use to make the predictions with. Okay, so that's our feature here, or sorry, our function here, which is going to take in the input and compute the full feature vector. So what we can see here is that the way I'm going to do it, just to show you how it's working, is we're going to go to this transactions fraud label online feature group, and this has some synthetic transactions that have been created already, and we're going to make predictions with one of those. So what we're going to do is we're going to get back this CC number, so the first credit card number from that particular group, and then we're going to pass in as well the current date time, and then we're going to just pass in some random amounts for the transaction, longitude and latitude, and then we're going to get back in this case the feature vector with all of the features that we need. And we can have a look at that on the next line, the one that it prints out. So these are the actual features that we're going to pass to our model, and we're just going to change them around a bit here into a format that's needed by the model, and then we're going to call predict on the model, and it's going to predict a 1 or a 0 depending whether it thinks it's fraud or not, and then we can get deployment logs. Now you can see it took about a second to get the result back. It said not fraud, and the reason for that is because the containers are deployed in Kserve. They can be swapped out and swapped in, so they're called Knative, which means Knative is part of it's called the serverless containers in Kubernetes. What it basically means is that if your container hasn't been used for 30 seconds or 60 seconds, it gets swapped out and swapped back in again, and then if it's in constant use, it'll just stay in memory and keep being used. But when it's not being used, then you can have this slightly higher latency on the first prediction until the container's been swapped back in. Okay, that's pretty much it. That's what I want to cover in this lab. They were all of the tasks that we did. We basically deployed our credit card model on Hopsworks, and we have a client that makes predictions on it. Now, there's a bunch of things you can do to improve on this. There is the PyTest notebook that we had from earlier. So PyTest workflow.yaml is a new file that's in the repository now. This is the GitHub action that you can use to run the PyTest program that we had from Lab 2. So the unit test that we have from Lab 2. And things that you can do, apart from adding that nice GitHub action, would be to build a nice UI for this. So build a Gradio UI, deploy it on Hugging Face Spaces. They have a really great free tier, so it won't cost you anything to deploy that Gradio UI. And then have users maybe entering individual credit card samples or generating random ones, and then predicting on your model whether they're fraud or not fraud. Now, you're not done. So one of the purposes of this whole course was to help you walk you through your first real serverless machine learning project. And we start out with Iris, and we've gone through this full credit card fraud example in quite some detail, all the way up to real-time fraud. But if you really want to do something novel, then build your own serverless machine learning project. Build your own unique one. Pick a novel data set. Pick a prediction problem for that data set. We have some great ones like air quality prediction, water quality prediction, water height prediction. People are interested in things like Bitcoin price prediction. Is Elon Musk in a good mood today prediction. There are a ton of novel prediction problems out there which could be modeled today because a lot of the data is available now in society. A lot of services have been digitalized. governmental services. We have obviously tons of data coming from many different sources. So you can build really useful prediction services with that data. You'll need to create a feature pipeline for it to make sure the data keeps getting updated. You'll need to have a training pipeline to train your model. You need to have some inference pipeline, either batch or online inference, to make the predictions. And finally, you'll need to have a UI as well and deploy this system in production. And then you'll have a great system that hopefully will add value to the world and be your unique contribution to the world of machine learning. With that, I'd like to wrap up and thank you for taking the course and thank you for the time for getting this far, and good luck with the rest of your adventure in machine learning. Thank you.